Hi, Honors Pre-Calc. Today we're going to be learning lesson 8.2, direct substitution within limits. The essential question today is how do you use direct substitution techniques to solve limits? And we're going to focus on this vocab, direct substitution. So you should already know the idea or the concept of substitution, right? It means we're taking something, plugging it in directly for something else. This lesson is really not going to be that bad, I promise. Here's what we're going to do. You're going to use direct substitution methods to solve limits, which includes understanding the properties of limits and solving limits of polynomial and rational functions. One example of something you'll be able to do is evaluate the limit as x approaches 4 of x squared. All right, let's just switch over to the notes and get started. All right, so we have a lot of words at the top of the notes, but it's not going to be that bad. First of all, direct substitution says, when the limit of f of x as x approaches c is simply f of c, then the limit can be evaluated by direct substitution. The limit as x approaches c of f of x equals L. That's our just definition of a limit. We've got some properties of limits here, which we're not going to get too much into today, but there's this idea that if we have a number multiplied by a function, we can pull the number out in front of the limit and just evaluate the limit of the function. If we're adding or subtracting two functions within a limit, we can separate them. If we're multiplying two functions within a limit, we can multiply the answers. If we're dividing, we can divide the answers. If we're raising to a power, we can raise the answer to a power. So there's lots of ways that we can simplify limits. Again, we're not going to get into too many of those today, but let's keep moving down the page here. We're going to be talking about limits of polynomial functions and limits of rational functions. Give me 1 second here to mute my notifications. Okay, here we go. So let's take a look at example 1. Find each limit. The limit as x approaches 4 of x squared. Now, for this question only, we're going to think about the graph to really remember how limits worked before, right? And x squared, we know, if this is our x and our y-axis, it's going to look like a parabola facing up, right? Now, there are no holes. There are no kind of corners, there are no breaks, there's nothing weird going on this graph. It exists as a continuous curve from negative infinity to infinity for its domain. So when we plug in 4 as an x value and try to figure out what the y values are approaching, it's going to be the same as if we just plug in 4 for x. So as long as our function is continuous near 4, we can just plug 4 in and call it a day. So it's going to equal 4 squared, or 16. The end. Let's look at letter B. 5x. That graph is continuous. It's a straight line. It has a slope of 5. So all we have to do is plug in 4 for x and call it a day. Let's take a look at the next one. Tangent of x over x. Now this is a fraction, right? And we know that in a fraction, we have problems if the denominator equals 0. But in this case, we're not plugging in 0 for x. We're paying attention to numbers that are close to pi, right? So that's not going to cause a problem. If we were trying to find the limit as x approaches 0, we'd have to do a little bit more work. Since we're looking at limit as x approaches pi, that's fine. We can just straight up plug in pi for x using direct substitution. So that pi will go in for both x's. The tangent of pi, if you take a look at your unit circle, you will find out that that is 0 divided by -1, so it's 0. The denominator is still pi, and that is going to equal 0. So that's our limit. If we graphed it, it would be continuous near pi, so that's why we're allowed to use direct substitution. Let's take a look at letter D. A square root of x for any numbers greater than or equal to 0, we can plug that in. If we have a negative number we're plugging in for x, we'd have a problem. But 9 is well into the positives, so we're allowed to just plug it in. Letter E, the limit as x approaches pi of x times cosine x. Cosine x and x both would be continuous, so multiplied together, they're still continuous. That means we can just plug in pi. And cosine of pi is -1, so we end up with negative pi. Letter F, the limit as x approaches 3 of x plus 4 quantity squared. This x plus 4 quantity squared is a polynomial doesn't have any corners or breaks or holes or anything. We can just straight up plug in 3 for x. And there we go. Okay. We've got one more set of examples on the back, and that is it. Quick lesson here. In letter A, we have x squared plus x minus 6. Like I was saying, this is a polynomial. There are no holes. There are no weird spots where we would have to lift up our pen or pencil if we were drawing the curve. It works. So we can just straight up plug in the -1. So -1 squared is 1, minus 1, minus 6 means this is -6. In letter B, now we're plugging in -1 to a rational function, a fraction with a polynomial on the top and on the bottom. And like I was saying earlier, we can just plug it in the -1 for x as long as that doesn't make the denominator equal 0. And in this case, plugging -1 in for x does not cause a problem. It's fine. Nothing bad happens. So we can just straight up plug it in. So we have -1 squared plus -1 minus 6 over -1 plus 3. Which is going to be 1 minus 1 minus 6 over -1 plus 3, or -6 over 2, so -3. Okay, that's how we do it. So all you're going to have to do for the worksheet is 1, check to make sure that the function is continuous near the x value that we're plugging in. 2, plug it in. That's it. That's the method of direct substitution. Hopefully that makes sense. Please let me know if you have any questions, and hope you have a great day. Thanks for watching.